everybody, and welcome to Math Blusters. Today's lesson will be focused on the fundamental theorem of calculus. Here we'll be doing two key things in this video. We'll be exploring what exactly the fundamental theorem of calculus is, and later on we'll be practicing some practice problems.
Okay, so what the fundamental theorem of calculus is basically saying is that the integral of the derivative of a function is just going to be that function.
But why is this true?
So let's just take the function y equals x. We'll create little rectangles. So our first one is going to be at 0 with the width of 0.5. Now if we plug in the function y equals x, we'll see that at 0 the height is 0, so we'll just leave the height as 0. Now here at 0.5 we plug it in, we get a height of 0.5, so we have a 0.5 by 0.5 rectangle, and then we'll just continue to do this for so on and so on, right?
But I had a question here. If you make these rectangles look like that, won't it actually underestimate the area underneath the curve?
Well, see, here's the thing. We can use smaller rectangles, smaller and smaller rectangles. So I can change this 0.5 to 0.25, and then even smaller to an eighth, a 16th, all the way down until infinity so that we actually approximate the area.
Okay, yeah, that makes sense.
But anyways, back to what I was saying. We can take these rectangles and we can put them on the graph, which adds up all of their areas. So our first rectangle, this empty rectangle, it has 0 area. So our second rectangle has an area of 0.5 times 0.5. Rectangle is base times height, so it will have a height of 0.25. Then our next one, it's equal to 1 times 0.5. So we'll add that, height of 0.5, that's the area, over 0.5. And you'll notice something. At 0.5, from 0 to 0.5, we'll see that the slope is 0.25 over 0.5, right? Which is equal to 0.5. Or more specifically, 0.5 times 0.5. Now, here, slope is 1 times 0.5 over 0.5. These 0.5s cancel out, so at x equals 1, we get the point on y equals x on this area graph, the one that's adding up all of our areas. So, if we get the area under the curve at some given point x, then it's the same thing as going to this graph and getting the slope at that point. Does that make sense?
Yeah, that makes sense.
So, shall we do a practice problem?
Yeah, I feel like it would be good to give a conceptual problem. I feel like I've understood the basics. I just need to see its applications.
So, one thing we can do, let's just take a triangle. We'll use the same function y equals x, but we'll have a base of 1, right? Using your typical triangle formula, this height would also be 1, right?
Okay.
So that's just 1 times 1 over 2, base times height over 2, which is equal to half. Now, let's try doing this with the integral. So what we'll do is we'll take the integral from 0 to 1 of x. We'll also add the dx because we were trying to find area. And so, can you think of a derivative, or a function whose derivative is equal to x?
Yeah, it would be 1/2 x squared, right?
Yes, half x squared. But now, what we need to do is we need to do half x squared, plug in the 1 to get, and then subtract it from 0 to get our area of a half, which matches our triangle formula.
But I had a question. Why are you subtracting the area when you plug in 1 from the area when you subtract in 0?
See, let's go back to this thing right here. If we wanted to define the area, say, between this number, 2, and this number, 3, we'd first have to find the area of the curve up to 3, and then we'd have to subtract that from the area up to 2, right? That way these two areas cancel out and we're left with just this area. Make sense?
Yeah, that makes sense. I feel like I have a good understanding of the conceptuals. Next, let's get on to some difficult and complex practice problems.
So, another problem that we can try is Gabriel's horn. So, what Gabriel's horn is we take this function y equals 1 over x, rotate it, so that we get this horn of a sort, and we want to find the volume of this horn. So, what we can do, we can take each of these circles find the area of it, and then stack it on top of the next circle infinitely so that we can get the horn. Because, as I believe you know, when we stack paper, it can get very tall, right?
But the problem is, how do we get it to like an x value of infinity? How does that work?
See, what we can do is we can just say take the limit as n approaches infinity of n and 1. We won't actually reach infinity, but we can get as close as we possibly can. Infinitely close to infinity, if you will. So, as we said, we need to find each area of the circle. That's pi r squared. So, pi, our radius, as I said, is 1 over x. Pi 1 over x squared dx, because we're finding the area. And so we have the integral of 1 over n as n approaches infinity of pi 1 over x squared. Now, my students, can you think of a function whose derivative is equal to 1 over x squared?
A function whose derivative is 1 over x squared would be x to the negative third, right?
No, that's if we're taking the derivative. We put this to negative 2, subtract 1, that'd be negative 2 x to the minus 3. You're thinking, what's the derivative of this function? But what we want is the other way around, right? What function, when we take the derivative, is that? Remember,
it would be negative 1 over x.
always subtract 1 whenever we do the power rule. So let's try to do the opposite of the power rule and try adding 1 instead. So, what function would have the derivative of 1 over x squared?
Negative 1 over x.
Yeah, negative 1 over x. Now, what function would have the derivative of pi times 1 over x squared?
Pi times 1 over x squared? It would just be...
What?
I'm not sure. How would you do that?
We've already said that it's 1 over x whose derivative is 1 over x squared, right?
Yeah.
Now, if we multiply a constant here, this would go here, right? Because if we have, say, 2x, right? Its derivative is just 2 times the derivative of x, right?
Yeah. Constants don't affect the derivative.
Yeah. So if I just add a pi here, I can basically say that pi times negative 1 over x, its derivative is pi over x squared, right?
Oh, yeah. I understand that now.
So, all we have to do now is just, we've got our antiderivative, negative pi times 1 over x, and we have to do it from 1 to infinity. So, we'll first plug in infinity, which is negative pi times 1 over infinity, and we'll plug in the other value, which is 1, so that's negative pi times 1 over 1. Now, do you see on how this is different? This isn't 0. This part doesn't always have to be 0. Instead, this part at the front is 0. So when we simplify it, we'd get 0 because 1 over infinity is equal to 0, and we'll subtract negative pi to give us a final area, or final volume of pi. So Gabriel's horn has a volume of pi.
But how does it make sense that if you take the limit at infinity, it's 0? How does that make sense?
Limit as n approaches infinity of 1 over n?
Yeah, how would that be 0 as if you put it into, like, for the area?
Well, as we plug in bigger and bigger numbers, it gets closer to 0, right?
It does, yeah.
Yeah, that's why this is approaches 0.
Oh, it could be like 900 million or like 900 billion, and it'll just be closer and closer.
Anyways, on to our next practice problem. For this one, we're going to be figuring out what the value of pi is, or the volume of Gabriel's horn. So, we have a circle. Now, what's the equation for a circle?
X squared plus y squared equals r squared.
Yes. We can rearrange this. Y squared equals r squared minus x squared. Y is equal to the square root of r squared minus x squared. And for this one, we'll set r to be 1, because the area of a circle whose radius is 1 is pi times 1 squared, or pi. So y is equal to the square root of 1 minus x squared. What we'll do, though, is we'll just take a quarter of that circle. from here to here, 0 to 1. So when we take the integral of that from 0 to 1 of root 1 minus x squared dx, all that would be, actually no, can you think of the antiderivative of the square root of 1 minus x squared?
That would have to use the reverse chain rule, right?
It's incredibly complicated. You can't, right? Fortunately, though, we can use the binomial distribution and get that the integral of this from 0 to 1, or that the binomial distribution of this is equal to 1 minus x squared over 2 minus x to the 4th over 8 minus x to the 6th over 16. Now, do you think you can get the antiderivative of this?
Yeah, it would be x minus 1/4 x cubed. Am I being correct?
It would be a third x cubed, except it's actually be a sixth x cubed because.
Oh, yeah. So it cancels out.
Yeah.
And then it would be, so you have x to the 5th power there, but you want to make sure there's an 8 on the bottom. So it would be,
I'll help you out a bit. It's 5 times 8, which is 40. And then we'd have x to the 6th over 102, right?
okay.
Now we want this area from 0 to 1. So we'll plug in 1 minus 1 cubed over 6, minus 1 to the 5th over 40, minus, or no, this is actually to the 7th, 1 to the 7th over 102. And we'll subtract that from us plugging in 0. So 0 minus 0, there's a 0 cubed to 0, minus 0, minus 0. This all is just 0, so our final answer is 1 minus 1 over 6 minus 1/40th minus 1 over 102, which is approximately 0.8. Now remember, this is the quarter of the circle, so when we multiply that 4, we get 3.2, which is pretty close to pi.
But I had a question. If you do the integral from 0 to 1, wouldn't it also count the bottom half of that circle that is also from 0 to 1?
Yes, you would be right to make that question, except the square root, it can't ever return a negative number.
Oh,
right?
Okay. And does this apply to all circles or just a circle with radius 1?
If we wanted to do all circles, like let's just say we do 4, we'd have to multiply this. This would be 4, which would be 4 minus, I believe, it would all probably minus 4x squared minus 4x to the 4th minus 4 to the 6th, which would just multiply the area by
4.
4.
Cool. Yeah, that makes a lot of sense. Thank you everybody for watching this episode of Math Busters. I hope you enjoyed the video, and just a quick recap of what we learned. In this video, we explored what the fundamental theorem of calculus is and gave a conceptual problem to deepen our understanding of it. Additionally, we also gave many practice problems, including the area of a triangle, the volume of Gabriel's horn, and finding out what pi is by finding the area of a circle. I hope you enjoyed this video, and don't forget to like and subscribe. Peace.